Alright, so today let's just look briefly at the graphic thought. Y'all ready for notes? Right? Alright, so in some problems, it'll be clear that there's a horizontal asymptote, because both sides of the graph flatten out. And whatever number they're flattening out to is your horizontal asymptote. And so, by looking at a graph, if it's not flattening out, you know it doesn't have one. But if it flattens out, like this one does, we'll just say that's at 1. Then this would be y equals 1 is my horizontal asymptote. Now, what would my graph of this basically be telling me? Well, the limit of x as it approaches positive infinity of f of x is 1, and the limit of x as it approaches negative infinity of f of x is also 1. So if I had a formula, I could do some math with it and prove that the graph did that on each side without having to graph. But if I have a graph, I can just generalize that if it's flattening out to 1 on both sides, that must be the horizontal asymptote. Now, let's look at an example that doesn't do that. A bit too much curve there. Alright, so in this problem, what could I talk about in terms of the limit to infinity and negative infinity? Well, first of all, I don't see a horizontal asymptote, I see a slanting one, which tells me that the limit of x as it approaches negative infinity of f of x is negative infinity, because this graph's going down forever on the left side. Would everybody agree with that? And then the limit of x as it approaches positive infinity of f of x is positive infinity, because my graph on that side is going up forever. Now, I'm really focusing on this arrow and this one because they're the furthest ones over. The other arrows are in the middle, and they have to do with that slanting asymptote thing. And I may not even have that asymptote really drawn in a really good place, but that's kind of what the idea is.
Will there actually be 2 asymptotes on that?
Well, you know, I was just looking at that. No, I think I've drawn my asymptote the wrong direction. I don't know if I can take that out. Let me see if I can. I think it's actually supposed to be on the other side of the graph. But I drew it in before I drew the graph, and I should have drawn it in after the graph. I think it actually goes this way. That makes more sense, because your asymptote should be against the sides that are in the middle, and your ends of your graph are what's going out to infinity and negative infinity in terms of the behavior of the end of a graph. So, you know, you can visualize with a graph kind of what it's doing. You can look at the formula and kind of know what it's going to do beforehand. So in your homework tonight, you're going to have some graphs that have been drawn, and you're going to have some formulas, and you're going to try to match them up without doing a whole lot of math, because you kind of know you could do some of those shortcut rules. Of course, if the shortcut rule doesn't work, you know, if you don't have a problem where you can take the powers in the front and figure out what they're doing, then maybe you could do a table and figure it out. Or maybe you could do the algebra and figure it out. But they've given you a graph to try to see if you can match up which graph would have the horizontal asymptote that they're showing. Or it doesn't have one at all, I guess, if it didn't have one. Alright, so that's the graphic thought. Now the table thought it's a 2-part thing also, because I need to know about negative infinity or positive infinity. The problems in the book focus a little too much on positive infinity and not enough on the fact that you could do it with either. So in my example, I'm going to do both. So because when we do our problems after we learn about this chapter and we get to section 6, we have a 10-step problem that shows that I can draw a graph without knowing anything about what the graph looks like, without plotting any points off the graph pretty much, except for the maxes, mins, and inflection points. And I can graph it pretty accurately if I know what the ends do and what the middle does. So the table method can be really good for that if you can't do the algebra method. Algebra only works if you can make fractions out of it. Well, polynomials, you can't make fractions out of them. And there are a few others you can't make fractions out of. So because of that, the table method can kind of be important. Now when you look at the table method, let's talk about the table method we looked at before. You know, we looked at, okay, there was a number in the middle, and that number in the middle, we looked at, you know, putting 9s and 0s on both sides. Remember that? Like, if I wanted to do 1 in the middle, I put 0.9, 0.99, 0.999, and then I did 1.001, 1.01, 1.1. Well, this table is different, okay? You're going to do like 10, let me start on this side. 10 to the 1, 10 to the 2, 10 to the 3. Isn't that getting huge quickly? Okay. And over here you're going to do negative 10 to the 1, negative 10 to the 2, negative 10 to the 3rd. And you could put more on it if you wanted to. But notice I'm not focusing on the middle this time. I just kind of left that box blank. I really don't need that box, so per se. And you might want more than 3 on each side, but sometimes that time that it takes to write so many of these gets kind of long. So I'm just going to show it with putting 3, but if that doesn't show me enough information, I can put more powers, because all I'm doing is upping the power by 1 each time. And as we do that, we're going to take a problem that we clearly know the answer to already, so that we can just visualize this table thought. So we're going to focus on what's it doing as it goes this way and this way. What's it going, and what's it going to? So in my first example, f of x is equal to 4x minus 2 and 3x plus 1. Now we know, based on the rules that we've discussed yesterday, what am I looking for here? What's the answer going to go to? 4/3? So that's what decimal? 1.3 repeating. Okay. So we should be seeing it's doing something to getting close to that. And sometimes you may need more numbers than this, and sometimes you may not. We don't know yet, so that's why we're looking at it. All right, so we're going to put this in y equals. We're not going to look at the graph. We're going to go to the table feature, and we're going to turn on the ask feature of your table feature, and we're going to type in the 10 to the first, 10 to the second, 10 to the third, and let's focus on the right side of this table first. Now, we're hoping that we'll see, and if you need a number in the middle, you could always put 0. If you just need a number in the middle, because 0 would always be in the middle of all these tables, but you don't have to have a number in the middle. So we're putting our formula in y equals and going to the table feature and turning on ask, because, or if you'd rather do the second count value button, you could do that also.
If you do anything for the middle, between the two things first,
I don't.
leave it blank.
I leave it blank. But you can put 0 if you'd like. That's the only thing you could put in there. So we're going to look up the value for 10 to the first, 10 to the second, 10 to the third. Now you might find it easier to type 10, 100, 1000. That's what that is, right? And if that doesn't show us clearly enough what we think it's going to do, then we can put in 10 to the fourth, 10 to the fifth, and keep going until we see what it's clearly going to do. So when we put in 10 to the first, what do we get?
1.2258.
1.22. All right, when we put in 10 to the second, what's it going to round to? 1.32. And when we did put in 10 to the third, and just out of curiosity, 1.4, 10 to the fourth would be 1.33 also? All right. So this clearly is going to 3 repeating. Because you're seeing a lot of 3s. Now we've checked the other side to see if it has the same answer. Because the limit of x as it approaches positive infinity of f of x is 4/3, or 1.3 repeating. If you're not sure about how to round them, you can always give a decimal answer and not get the exact. We just want to make sure that the other side, the limit of x as it approaches negative infinity of f of x, has the same answer. So what is negative 10 to the first power? 1.45. And negative 10 to the second power? 1.34. And 1.33 again. So it's going to 4/3 on this side as well. And it's very clear that both sides are going to the same number on the outside of my table. So instead of them going to the same number in the middle like we did before, now we want the two ends to be the same. Now, we can put in a problem that doesn't do that. It's not hard to come up with a problem that doesn't do that. And to prove that to you, instead of putting in a fractional problem this time, I think we'll put in a polynomial problem so that we can see it with that, because that's what we're going to be doing when we get to section 6, is doing it with polynomials. So let's do just something simple like a quadratic that we know what it's going to do. Suppose f of x is equal to negative 2x squared plus 1. Now we should know which way this graph is going because it doesn't have a horizontal asymptote. We know that because it's a quadratic. Which way is it going? On the ends of the arrows. Down, because I reflected it, right? So our table should show it's going to negative infinity. Both sides, they're doing the same thing because it's a quadratic. So we put our numbers in with these really large increasing x values. And by using these large x values, it makes us have to put less than the table. We don't have to do a huge amount of them. Although, I think our textbook does a lot more with their table than I'm showing you right here because they're only doing one side. Alright, so go ahead and put this in your calculator and get your table filled in and show as it goes to the left or goes to the right. They're not going to the same thing, but see if they show they're both going to negative infinity, because that's what we said before we started the problem, that we think it's going to do. Wow. Well, yeah, that makes sense. The two arms are going the same way. Now, if our two arms are going different ways, like a cubic graph, I wouldn't expect them to be the same numbers, although they might be, and just want some of them positive, some of them negative. That's one of the things about using the same numbers on both sides with positives and negatives, is you might get similar numbers, but they may not always be the same sign. Okay. So, are your numbers, when you're doing the positive side, increasing rapidly or decreasing rapidly? They're getting more negative really quickly? And if it didn't show like that, you could put more on your table Because sometimes you might need to add a couple more columns for it to show clearly that it's going to rapidly decrease. So what kind of numbers are you getting on the positive side? Negative what? 199. Oh, okay. And what's the next one? Alright. So those definitely show it's getting negative to negative infinity very quickly. So our limit of x as it approaches positive infinity of f of x is going to negative infinity. Because my graph's going down forever. Is it doing the same thing on the other side? With the exact same numbers? Alright. So for the negative infinity side, we have the same numbers, and it's going to negative infinity. Well, that makes sense if you think about it, because here's my graph, and it's doing this. It's pointing towards negative infinity forever on both sides. It's a quadratic. So this is a way that you can show somebody without doing any algebra work, because I can't do algebra on polynomials. They don't have fractions in them. And I can't use conjugates because it's not a radical problem. So I can use the table method to show my math and show where it's going to. All right, a couple other odd questions. We've talked a little bit before about the squeeze theorem. And I kind of keep trying to reiterate that the squeeze theorem is a great way of determining a limit. So the limit of x as it approaches infinity of sine of 2x over x see, this is not our rule. The rule for sine with the number in front of that x has to have the number in front of the x on the bottom, first of all, and it has to be going to 0. If I had sine of 2x over 2x and I was doing the limit to 0, it'd be an answer I could come up with. But because this one is going to infinity, this is not something I just can look at and put x's under it like I did the others either. So one way you can do it is from a graphic point of view called the squeeze theorem. And to do the squeeze theorem, you take out the more simplified part of the problem to make a simpler function and squeeze it on the original problem between the two. So we're going to squeeze it between negative 1 over x, the limit of this as it goes to positive infinity, to the original problem, to the limit of x as it approaches positive infinity of 1 over x. And usually this is written with less than or equal to marks between these. If I can squeeze the original problem between negative 1 over x, which is one of those rational functions, and positive 1 over x, which is another rational function that fits quadrant 1 and 2, 3 and 4 would be covered by all of these, because the negative 1 over x would be in 2 and 4, and the positive 1 over x will be in 1 and 3, and this would be somewhere in between there, and squeeze it. So we kind of set it up like that to think about, we want to do the limit of each one. Now we know what the limit of this is based on our rule. We know it's 0. And we know the limit of this one over here also would be 0. So guess what the middle one is? The answer is 0. Because we just sandwiched a function that's a little more complicated looking between two functions that are both 0 because that's part of the function. And so that's what the squeeze theorem is all about. It's just trying to take away the simpler part and look at it first, because that can give it away. Now, we could have graphed all three of them and looked at it like we did before and seen what it did. But I know right now that the negative 1 over x is here and here. And I know the positive 1 over x is here and here. And then the sine of 2x over x, I have no idea what that looks like. I really don't. But I'm sandwiching it between these, so I know it's going to fit right in here. More than likely. So if it fits in there, then, are you putting it in, Destiny?
It does like a regular.
Here, come up here and draw it. Yeah, let's do it in a different color. All right. Then that proves it, because what it's going to do is keep doing it until it kind of does this. Does that make sense? It's going to flatten out to 0 because it gets closer and closer. As these two lines get closer together, it's going to flatten to 0. So the key here is the sandwich theorem can give you that without having to do a lot of work, because you can do it for piece of the function. There's another method if you're having trouble with a function, and that's called the substitution method. And the substitution method is a way of changing the problem from being about infinities to being about a number we can work with. And we haven't really done this method before. It's a little strange, but it works pretty well. Suppose I want to do the limit of x as it approaches infinity of 1 over 2x plus sine of x. And that's not something I'm typically very familiar with in terms of our problem. Well, actually, this wasn't the substitution one. This was just one outright. I'll come back to the substitution in a minute. I didn't realize I had this one written up there. All right, let's talk just for a minute about each individual piece of this problem. Now, we know sine's a wave. Stays between 1 and negative 1, right? And then we add a 2x to it, which is linear. So this is like you've got a power problem. You got a trig. And you got a constant on the top. Now, sine's never going to get bigger than 1 or negative 1. But 2x is going to continue to get large, is it not? And then I'll add 1 or negative 1 and just make it 1 more, or take 1 off. And then we're going to divide that into 1. So maybe we need to be thinking about as that denominator gets larger, right? As you take a number like 2x and it goes to infinity, it's going to keep getting bigger. Everybody agree? And then when you add the trig to it, it's just going to make it a little bigger, a little smaller, but it's still going to be big. But what happens when you take a problem and the bottom goes to infinity? Well, let's just think about some numbers here. When it's 1 over 1, it's 1. When it's 1 over 2, it's a half. 1/3, 1/4, 1/5, 1/6. What's happening to my fraction? Well, eventually, when it's 1 over a million, 1 over a trillion, 1 over a gazillion, what's it going to? Huh? 0. Think about it. It's getting smaller. From a half to a fourth to a 16th to a 32nd. Eventually it'll get so small we can't see it. It's going to 0. So sometimes you can reason out your limit based on the math that happens in the fraction by put some numbers in there. And so this one, the answer is 0 because this fraction is going smaller and smaller as the denominator goes to infinity because the top was a constant.
So is that how it works for every problem in this infinity?
Mm-hmm. Yep. All right, now we'll look at the substitution problem. Because it was kind of, they're both trigs, so therefore I wasn't paying attention that it was two separate problems. All right, so the problem in this one is that I've got x, which is going to keep getting bigger, and I'm multiplying it by psi, which has 1 over x in it, which keeps getting smaller. So there's this method called the substitution method. And it allows you to change the perspective of the question. And it varies a little bit, but this one kind of gives away a little bit of a hint to it, because it sure would be nice if this wasn't a fraction. So take any variable that you'd like and set it equal to that. They usually use t. I don't know why, but they do. But you could actually use any variable. And we're going to do the substitution of it. This is called the substitution method. Because we're going to say 1 over x is equal to t and take that 1 over x out and put a t in for it. Now we already know that this fraction goes to 0, right? So by taking that 1 over x out and putting t, it's going to change what my limit is. And then I need to take this x out. Well, if you remember anything about math 2, you know that proportions can be turned around in different ways. You can switch the diagonal on a proportion and solve it for the other variable really quickly. So I'd like to take the x out and put 1 over t in. And granted, I know that puts a fraction at the front, but that's okay. It's better that it's in the front and then in the trig. So now we're going to change our limit. Our limit no longer is about x, it's about t. And because our original thought was t is equal to 1 over x, as x increases, that goes to 0. It changes our limit to t is going to 0. What would it do? And we're going to have our problem as 1 over t sine of t. So we're substituting in some much nicer math to work with, because now the fraction's not in the trig, it's outside the trig. But that changed what our limit's all about now. So we had to understand that if this whole fraction is t, as x goes to infinity, we just talked about in this last problem, that whole thing goes to 0. So that changes my limit to be 0. And then, if you put those two together by multiplying them, you get sine of t over t. And that's one of those special trigs we learned about in the first chapter, that when trig goes to 0 with this fraction, the answer is 1. No work to do for that. It's a rule that the limit of t as it goes to 0 of sine of t over t is always 1. So being able to do the substitution method, it's not the algebra method, but it's doing algebra. But it allows us to turn the problem into something we can work a lot easier. I also could have done the table method on this one, and it would work also. All right, the last thing we're going to look at today is, in this section, they kind of want to pull everything back together and say, what are all the important features that graphs can have from anything you've ever learned about graphs? That's a lot of stuff, isn't it? We better make a list. So we're going to find extremis, if it has more than one. Intercepts, because x and y intercepts are very important places on graphs. It makes our graph cross the x or y axis, which is important to know where that happens. We're going to look for, is there any symmetry in the problem? Because if the left and the right are the same, that would be a whole lot easier to work out the question. And we're going to focus on those asymptotes that we have just been discussing. And we're going to get all of this and hopefully be able to pull something together to make a decent problem. And we're going to do 2 of these, I believe. Yeah. All right, the first one's a really simple equation. Not real keen on how they wrote the problem, but okay with it, I guess. So one of the things that we're going to focus our attention on in our lesson 6 is pulling together everything we've learned from lesson 3, 4, and 5, along with other issues that we may need, like intercepts. So we have already learned that when you have a rational function, if you set the top equal to 0, it makes extremas, like maxes, mins, or inflection points. And if you set the bottom equal to 0, you would get vertical asymptotes. But that has to be on the derivative, right? Everybody agree with that? All right. So that's part of our process of looking for different things. Now, let's start off with actually getting that derivative. And to save a little time, let's just get it on the calculator so we don't have to spend a tremendous amount of time. Because we want to find those critical numbers, if there are any. Who knows? You know, there's lots of different kinds of critical numbers, but there might not be any maxes and mins on this graph. I don't know. But we got to check. What are you getting? What's the formula?
3 over x minus 1
All right.
Almost have something to say.
Yeah, it's evaluating for you. All right, so the first thing you do when you're thinking about critical numbers is you look for those extremas, the maxes and mins, and that happens when the top's equal to 0. So if you think about it, is 3 ever going to be equal to 0? No. So that means we're not going to have any max or mins that are extremas. Okay, extremas are always maxes and mins. Critical numbers adds other issues to that. Extremas are one kind of critical number. You got vertical asymptotes and cusp and all these other kinds of critical numbers, but they're not extremas. So this problem has no extremas that we can tell. Or at least no max and min extremas. Wonder if we should do, well, no, we won't do that. We'll just move on. All right, so now let's talk about asymptotes. There are two kinds of asymptotes that we have studied. The first one is what you get from setting the denominator equal to 0. That's how you get vertical asymptotes. And of course, if I set my denominator equal to 0, I don't need the square on it. Because I could see in the first problem that 1 was going to make it 0, right? You can look at the original problem or the derivative and tell that's an issue. Then to do the horizontal asymptotes, we want to do the limit. And we'll just do the positive infinity one for right now because it don't matter if I do the negative or positive. I mean, it's going to give me the same answer on both of them. But when you do this in section 6, you're required to look at writing out both. The math would be the same, though. Okay, so you take the original problem and you do what? What am I going to put under all of them? Okay, lowest power is x. So that means that the limit of x as it approaches infinity of 2 over x plus 1 over 1 over x minus 1. So these two go to 0, so 0 plus 1, 0 minus 1 comes out -1. Now let's go back and look at the shortcut rule. Here is the highest powers. Would this be -1 since they're equal? 1 over -1. -1. Because I can't look at these. They don't have X's on it. You have to look at the highest power. That's why I don't like this problem, because it's out of order. All right, so we got our, let's see, what else are we looking for? Intercepts. All right, let's talk about your intercepts. Some of you may have forgotten about intercepts and how to find them. To find the y-intercept, you plug in 0. That's pretty easy. The original function, which comes out 2. So I've got the y-intercept is 2. To find the x-intercept of a problem, you set the function equal to 0. Now in this case, that's going to be a fractional problem. So I'm going to have 2 plus x over 1 minus x equals 0. Now if I cross multiply, the denominator goes away. So just like finding critical numbers is setting the numerator equal to 0 to derivative, you set the numerator equal to 0 to find an x-intercept. Because when you cross multiply, that's going away. So x plus 2 equals 0 makes x equal to negative 2. So my x-intercept is negative 2, 0, where my y-intercept is 0, 2. All right. Now, the last thing they ask us to figure out is if there's any symmetry. And sometimes you can tell whether there's symmetry or not by doing some algebra. But we may decide about symmetry here by just looking at the graph, because we've already done a lot of algebra. So where was our vertical asymptote again? How much? Positive 1. And where was our horizontal asymptote? Negative 1. And then we have a y-intercept of 0, 2. And we have an x-intercept of negative 2, 0. And they're both in the same area. So I'm going to have some problems because I'm going to have a graph up here that I've got 2 points for, and I have nothing down here. Or nothing over here, or nothing over there, depending on where it ends up. No problem. We'll just get some stuff here in a minute. Now, the last thing that you probably want to do is look at a couple of things in terms of limits with tables. But since I've drawn my graph, I'm just going to erase a little bit of this to have room to put it. All right, so we've got everything drawn so far that we can tell from what we found. So to find out about symmetry and to find out about the end behavior of your graph, let's first do the limit to did I do that already? Oh, I did that. To 1. We want to look at the limit to infinity of 1 of f of x. Because 1 is where our vertical asymptote is. We want to see what it does on both sides of 1. So this goes back to the table method that we discussed earlier, where you put 1 in the middle and you do the zeros and the ones. Well, I got an extra box. Should have squeezed those so close in there. Okay, so we're going to put the original problem in our calculator. We're going to go to table and look at the behavior on each side of 1, because if they're going to round to the same thing, then, or going in the same direction, then we'll know it has symmetry. And if they're going in totally different sets of numbers, then we'll know it doesn't have symmetry. So your limit on each side of your vertical asymptote can tell you about symmetry. Alright, so now don't tell me the answer at 1 because I don't want to know what 1 is. I want to know what it's doing on each side. So what's the 0 side doing? What numbers are we getting here? Huh? 3001. Alright, so that sounds like it's going to negative infinity. Does everybody agree with that? Because as you go to the middle of the table, they're getting more negative. Alright, what's this side doing? So positive, same numbers? Alright, so very similar. And not 299 and what? 29. Okay. So, must have something to do with 3,000. They're so close to 3,000. It's weird. Alright, but this side, as you go to the middle of the table, is going to positive infinity. So, if one graph's going up and one graph's going down, is that symmetry? Well, might be. What are the kinds of symmetry? Maybe that's what we should have been discussing first. There's more than one kind of symmetry, right? There's the y-axis symmetry, where half of it's on each side. There's x-axis symmetry, where half of it's on each side. And then there's origin symmetry. So this one's origin symmetry? No, but it's shifted origin symmetry, kind of, right? It's more like the origin symmetry, but it's shifted. So it looks something like that. And so we've proven, and it really doesn't have symmetry because it's not at the origin. Okay? It doesn't have, we don't have a name for symmetry if they shift it. So, symmetry would say none. But it's that simple. You can use all this information and you can tell a lot about it without having to actually look at the graph. Now, I also could have done the some other things probably to do this limit. But that was the best thing to do because of it being a vertical asymptote where I'm doing it is to do a table. Because it's the quicker one. Alright. Now, this one didn't have a critical number. I think we should at least do one that does. So we're going to do one more of these. And then we'll be done. So the first thing you should always do is do a derivative. Because if you do a derivative, and actually we're going to, in this problem, we're going to twist it a little bit on our derivative. So dy over dx, we're going to take the derivative twice. This is going to give you a lead in on tomorrow's lesson. So I want you to type this in the problem and take the derivative once, and then I'm going to tell you how to get the calculator to do the derivative a second time easily. This is what y'all typing in, right? For your derivative? Okay. To get your calculator to do the second derivative, you put comma 2 out here and it takes 2 of them and it does the derivative twice. I didn't know that for a long time. I thought putting the 2 out there plugged 2 in. I kept trying to figure out why it was giving me all these crazy answers and not doing what I asked it to do one day, and then I finally realized what the 2 did. All right, so what was the first derivative? I know it's got a squared parentheses on the bottom, right? What's on top? Plus 4? X squared plus 4, negative on the outside? Okay. And then when you take the second derivative, I know it's got the same thing on the bottom, but what power is the bottom? It's cubed. All right, what's up top? All right, so first of all, we're looking for critical numbers. So in these problems, we're hoping that they'll show some extrema. And then we'll try to get the other critical numbers that we need from vertical asymptotes. All right, so to find critical numbers means to set the numerator equal to 0. So if I divide that negative off, that's not going to make any difference in the question, right? When was x squared plus 4 ever equal to 0? When can you square a number and get a negative so it'll cancel a positive 4 out and give you 0? You're shaking your head no. Why? You can't because it's imaginary. Right? For it to work, it'd have to be x squared minus 4, because then I could move the 4 over and square root it. If I move that 4 over and make negative 4 out of that, right, the square root of this is imaginary. So there are no maxes and mins in this problem. Does everybody see that? Now let me show you just briefly how this problem with the second derivative is going to show me something. So I have 2x, x squared plus 12 equals 0. Now, you set each one of these equal to 0. Based on what we just discussed on the previous part, what do I know about this problem right now? The parentheses can't equal to 0. Okay. So then that means x equals 0 over here, because I can divide by 2 and get 0, right? Now let me tell you what we just found. And this is kind of a lead-in on tomorrow's lesson. A second derivative tells you there's an inflection point. And it's at 0. So we have an inflection point on this problem. Now, with vertical asymptotes, we might have some other critical numbers. Granted, they're not extremas, but another critical number. You see, the extremas have to be your maxes and mins, inflection points. Those are important to know. But vertical asymptotes are critical. So in the original problem, I had x squared minus 4 in the denominator. If I set that equal to 0, what can x be? All right, then it's going to be plus or minus 2, because you square rooted something, right? We always put plus or minus on square root. So this problem has 2 vertical asymptotes and an inflection point. Now we got to get some horizontal asymptotes to see, is it flattening out, or is it doing one of them funny things where it goes off and does some slanting asymptote? So with horizontal asymptotes, the limit of x as it goes, let's do positive infinity, of x over x squared plus 4. So what am I going to put under, everybody? X squared so once I put x squared under, everybody, my limit of x as it approaches infinity becomes what on the top? 1 over x. And on the bottom, the first fraction? 1. And on the other one? Just the same thing. So that becomes 0 over 1 plus 0, which is 0. Which tells me that I could have got that over here because the top power is less than the bottom power. So now I know my horizontal asymptote is y equals 0. Now the next thing I have to find is my intercepts. And with my intercepts, let's see. Let's do the y-intercept first. I always like to do y-intercept first because it's evaluating. We're going to plug in 0 in our function. So the original problem would be 0 over 0 squared plus 4, which is 0. So not only is 0, 0 an inflection point, but it's an intercept. It's also the x-intercept. Right? It's the y and the x-intercept because I'm at the origin. Only place on the graph where you can be both. So I don't need to calculate the x-intercept because it's the same number. Alright, so now let's graph what we've got so far. First we had two vertical asymptotes at 2 and negative 2. And we had a horizontal asymptote at 0. And we got a big intercept that we know is an inflection point in the middle of our graph. That's what we know so far. Everybody with me so far? Now, because my graph is broken into 3 parts, my symmetry is going to happen to each, if there is any, is going to happen on each side of this. Okay? Because that's what the whole graph's centered at. Because I have 2 vertical asymptotes, I can't do the vertical asymptote way. You can only have 1 vertical asymptote and do the table thought. I can't do that with 2 of them.
This is the pattern. It's like 3 different parts.
That's right, it's 3 different parts. So it might be easier to visualize the symmetry once we get it drawn. So if we hit graph, if we type this in y equals and hit graph, it would give us a visual. Well, I'm just going to draw it up. Pretend we did that. And this is what we have. So that's why it wouldn't be a really good idea to look at symmetry with our table thought like we did on the previous problem, because the 2 vertical asymptotes wouldn't show the symmetry. The symmetry is all based on the center of the graph at the origin. Now what kind of symmetry do I have? I have origin symmetry. Because these 2 pieces flipped over the origin and these 2 pieces are flipped over the origin. So sometimes you just have to visualize symmetry. Sometimes there's not some math we can do. Well, let me rephrase that. That is not true. There is some math we can do for that. Yeah. It's not the same math, though, is the last question. The values of this problem have to be done with that. We did this in pre-calc. You put negative on x and y and see what happens. So if I put negative on x and y, that'll put a negative on my y here, a negative on my x here, and a negative in my x squared. Everybody with me so far? This goes back to pre-cal. So I can't do a table symmetry. Now the way I'm showing you right now, I actually could do all the symmetry problems this way to see if I have symmetry. This might be a better way of doing it to see if the 2 sides of your graph are going to be symmetrical with what kind of symmetry. This is just one of them. This is my origin symmetry test. If you put in negative x or negative y only, it's the x-axis or y-axis symmetry. But if you put both of them are negative, it's origin. We did it in proof form. So first you square out the negative. That got rid of that one, right? Now, the best thing is to get rid of the negative on the y by multiplying by -1 on both sides, which does it to the top only, because it's like -1 over 1. And I get back the original problem. And if you get back to the original problem, yes, it has origin symmetry. And I can see that from the picture, and I can prove it with the algebra. So that's something we learned to do back in pre-cal. Now, if I want to see what each side of a graph is doing on a vertical asymptote, I do a table. It might not show me symmetry across the whole problem, but it might show me, is it symmetrical on each side of my vertical asymptote? That's a different kind of symmetry. What was you trying to plug it in to do?
Just show me the original graph. So it'd be like a straight line and then a straight line.
Okay, I'll come look at that. All right, so let me assign the homework real quick, and then I'll come look at your calculator. All right, so tonight on that same page we did last night, page 193, there are 6 questions at the beginning that ask you to match the graph to the vertical asymptote without using your calculator, which means they want you to do the algebra, to put the x or the x squared or whatever you got to do the algebra. So I actually want y'all to try all 6 of those, even though I'm assigning some odd ones, so you can practice a little bit of algebra.
Which numbers?
All right, so this is 1 through 6. Then I'm going to have y'all practice some questions using the table method. But these you can't look at ahead of time and know what it's going to be doing. And this is going to be from question 32 and 34 only. Just to let you practice a couple of table ones. And they're only doing the positive side. They're not doing the negative side. And then I'd like y'all to do at least a few of these, like this last question on the board. So, but I don't want them to be too nasty. So let's just do 36 and, well, wait a minute, before I say that, let me look at the answers for those. I want to see what the graph looks like. I want to pick one I know what's got. Okay. Oh, okay, I might have to sign 3. All right, 36 will work, and 40 will work, and 42. 36, 40, and 42. That will work for what I want. And we'll check this tomorrow and get into how do second derivatives work.